Hello and good evening. It's very interesting why that pops up first. Hello, Mukul. By the way, let me know if I'm pronouncing your name wrong. I'm not. How are you doing? I guess usually I take Fridays off, but tonight some people asked some questions, and I figured why not. I'm also doing a review for some students from a Calculus 2 class at UC Urban. Hello. How can I help you all this evening? What classes are you in? Let's take a look. What questions do you have? Let's see. You know, I was looking at kind of an interesting calculus question the other day. The last three. What are we up to today? I don't know. Someone is asking for the last three questions from linear algebra? Okay, sure. Linear algebra? Let's look. Where's linear algebra? What are the linear algebra problems? Is it the Vanderbilt matrix? The set that starts with that? Is that the set that you're interested in? The last three problems? Like, what is this, Markov chain stuff? No? Well, feel free to perhaps go ahead and share what you're wanting to look at in the Discord, in the linear algebra channel of the Discord, and we can take a look. Half and half. Oh, okay. I can also do the linear algebra set. I assume Emily is asking about the linear algebra set from York. The last three. Sure, well, feel free to share whatever you like. But this one looks like V1 is equal to 5 and 3. V2 is equal to, what, -4 and 1? And then they're asking about a V1 plus V2. Well, you should know that, so this corresponds to lambda 1 is equal to 2. Lambda 2 is equal to -2. So this is just, by the definition of linearity, this is equal to AV1 plus AV2. And you know that because it's an eigenvector, you have a very special property that AV1 is equal to lambda 1 V1, AV2 is equal to lambda 2 V2. So from there, you should be able to figure that out, yeah? And similarly with a negative 2 V1, you should be able to just pull the negative 2 out due to linearity, right? That's what it means for it's a scalar. So you can just pull it right out. And AV1, again, is equal to lambda 1 V1. Why? Why for which question in particular? Like the fact that it's a matrix transform means that it's going to be a linear transformation, which is why you're allowed to pull these things apart. A1 V1 plus V2 is equal to AV1 plus AV2. Why is A equal lambda? Well, this is what it means to be an eigenvector, right? Look up your definition of eigenvector. This is saying that for an eigenvector V, AV is equal to some lambda V, where here A is a matrix, and over here lambda is a scalar. The idea is that eigenvectors are very special vectors that when a matrix is applied to them, it's as if the matrix is just being stretched or shrunk. So go play through with those ideas. Yeah. Emily was asking about the Vanderbilt stuff. Vanderbilt stuff. We looked at this before. Use parts A to compute the determinant of V4. Show that V4 is equal to LU. Use part A to compute the determinant of V4. Okay, so remember that the determinant of AB is equal to the determinant of A times the determinant of B. So, okay, sorry, there's even a part A, right? So I think even earlier you have to show that V4 is equal to L times U. And I don't know, I don't think there's anything to it. Just multiply it together and show that it's equal to the claimed Vanderbilt thing. Yeah. It should be a pretty straightforward multiplication. Might require a bit of tedious calculation, but shouldn't be bad. And then part B is basically saying, okay, well, show that you should know that the determinant of a product is the product of the determinants. And this should give you a very easy way to calculate what you like. And then if you have A1, A2, A3, and 4 are distinct real numbers, then there exists a unique polynomial of degree at most 3. Yeah. Just look at that bit about polynomial interpolation. It should, yeah, this sounds vaguely familiar. A1, A2, and A3, and A4 are distinct real numbers, and there exists a unique polynomial of degree at most 3. P of x degree is less than or equal to 3. So PA1 is equal to B1, PA2 is equal to B2. Yeah, that should just be some theorem regarding polynomial interpolation. It should fall right out of that theorem, so go read it. And if you're being asked to find the unique polynomial P of x at degree most 3, satisfying, you know, some numbers generated out of your own ID, I'm pretty sure that polynomial interpolation part should give you all the information you need to go through the process. I think it's probably just something relatively simple like putting something into reduced row echelon form. Should not be crazy. Anyways, Emily, what questions are you interested in specifically? You just told me that you wanted to see the linear algebra questions. Anyone? What do you want? Random questions, textbook PDFs, algebra. Yeah, I can take a look at the physics questions too. Sorry, let me look at this linear algebra thing. What page is it on? Linear interpolation, page 163. Yeah, you've got a theorem guaranteeing the existence of a unique polynomial, so use that. And then it talks about how you can what is there something funny about find the unique polynomial of degree at most 3 satisfying this thing? It seems like the book gives you some methods to find the polynomial. Yeah. And consider the determinant. Okay. Yeah, they gave you all the tricks you need. Someone said something about a physics channel. Someone said something about a physics channel. What is it? Ah, yes. Let's take a quick peek. Yes, Emily, I'll take a look at number 3 in a moment, I guess. This problem I had some hard time interpreting it. It sounds like a rail car is moving along a straight. Okay. It's 200 kg at the start. And what is it moving at? 5 meters a second? Find the final velocity of the car in each case, assuming... Okay, so what are they doing? They're throwing an object with 30 kg is thrown sideways with a speed of 2.5 relative to the car's initial velocity? Sure, I'm happy to discuss. So what is that? I'm having trouble exactly getting from the wording, but it sounds to me like they're basically saying they're throwing an object out this way, which, to my understanding, should not affect... Oh. I think that if it's being thrown out this way, meters a second. And if there's an object being thrown out this way, that's what, 30 kilograms, I mean? Well, this means that by conservation of momentum, then the rail car has to have some velocity going this way. Yeah? Assuming that the handcar does not leave the tracks. So that's really weird, because if it's on a rail car, yeah, no, I mean, it sounds to me like whatever velocity is just going to get absorbed by the track, so this thing is still just moving forwards. So, like, if I'm interpreting the question right, it's just being thrown out to the side. You know, think about whether or not this would even change the velocity of the rail car. Yeah? Okay. You see what I'm getting at? The 1DC? Like, if you're throwing something out horizontally, think about how that would actually change your velocity, if at all. Okay. So Emily is asking about number 3. Yeah, Mukul, what is your calc question? I will take a look at linear algebra number 3 in a second. So what is it saying? Find a formula for xn that satisfies the recurrence. Xk plus 2 is equal to a minus 1. Ak plus 1 plus a xk. Or k is greater than or equal to 0. So a k plus 2 is equal to a minus 1. A k plus... what am I doing with my numbers? A minus 1, xk plus 1 plus axk. Find a formula for x of n. In application to linear recurrences. With the following initial conditions, x0 is equal to b, x1 is equal to c. I mean, it sounds like the textbook is just going to have a guide for you to do what you'd like. Right? I don't know what the next... What page is this? 3.4 of the textbook on application to linear recurrences. I mean, I'm going to go ahead and bet that it's going to walk you exactly through how you want to do this. Linear recurrences. Okay. Section 3.4. I'm scrolling and scrolling and scrolling. I just don't know how to approach it. I read the textbook and it didn't help. Okay. Let's take a look. Oh my god, this chapter goes on forever. Okay. Application of linear occurrences. Find a formula for xk when x0 is equal to 1, x1 is equal to 3. Okay, sure. So x0 is equal to 1. I'm looking at example 3.4.2 in the textbook right now, and it's walking through an example where they set x0 and x1 for some specific values. What do? They basically write out a couple terms, right? And they just start doing inspection because it's obvious. But then for a different x0 is equal to 1, x1 is equal to 1, it's not so obvious. And now they're going to use matrix techniques to try to solve this. The idea is to compute the sequence v0, v1, v2 of columns instead of the numbers. Okay. So vk is equal to xk and xk plus 1. Ooh, okay, that's kind of neat. It seems like we have some kind of trick here. So then this means that v0, well, what is it for our specific problem? It's going to be equal to b and c, whatever the b and c are generated by your ID. Yes? Okay. And the numerical recurrence, okay, it gets transformed. Okay, so then we just basically have to turn this thing into a numerical recurrence. Yes? So look at their example. Their example was when the recurrence was xk plus 2 is equal to xk plus 1 plus 6xk. They turned this into a matrix that looks like vk plus 1 is equal to xk plus 1, xk plus 2 equal to, oh yeah, you see how it is? The xk plus 1, 6xk plus xk plus 1. And this just becomes this starts to look like a matrix, 0, 1, 6, 1. So we basically have to figure out how to make a matrix, yes? Find a formula. And this matrix should hopefully lead us to a formula times xk, xk plus 1. So this is our A. So thus the columns are a linear dynamical system, so 3.37 applies where the matrix A is diagonalizable. Okay. Now they take A and they get the eigenvalues. So they grab the eigenvalues with corresponding eigenvectors. Okay, you can go through that process and do it yourself. Since P is equal to x1 and x2 is invertible, it is a diagonalizing matrix. What is that question? P is 1, 3, negative 1, 2. Oh, that's just the eigenvectors put together. Hopefully, I mean, I assume your situation it's going to be invertible as well, but it's just the eigenvectors. 2 by 2 matrix of the eigenvectors. Okay, it's a diagonalizing matrix for A. The coefficients bi are given by theorem gives us that equating the top entries yields. Okay, yeah. So I mean, look, it's exactly the same process. I think you just got to follow through this example, right? At some point, you're going to end up with some expression xk and xk plus 1. So I'm looking at the example right here. It's going to be equal to some like b1 lambda 1k x1 plus b2 lambda 2 to the kth power x2. So just, go through the example. It seems like it's literally the same as one of your examples, right? And the idea here is that at some point they just start equating the top entries together in order to get the expression. Plus negative 2/5 minus 2 to the k, negative 1 and 2. Yeah, and they basically just equate all the top entries together, including all the coefficients, and that's your expression for xk. It's a nice closed form expression. Yeah, I think you just gotta, doing the problem through is, for me, I think would be a little bit redundant because Well, doing it all the way through would be a little bit redundant because it's more or less the exact same process. As what you have in the textbook. Yeah. The next linear algebra question from half and half. Yeah, so if you have a couple of vectors that are just v1 is equal to 0 to -1, v2 is equal to -1, -3, 0, v3 is equal to -2, 0, and 3. Well, the first thing it asks you to do before you even do anything fancy is just figure out what linear combination of v1, v2, and v3 will yield x. So this should be something you know how to do. You basically need to figure out a linear combination of these fellas and figure out how to get that to add up to x. And that should just be, using an augmented matrix, reduced row echelon form, right? That's basically like saying v1, v2, v3, and x. Just use reduced row echelon form. Use reduced row echelon form to figure out what coefficients you need. Yeah? That's I mean, honestly, you could just do it by inspecting x, v1, and v2, and v3. It shouldn't be too hard. Yeah? Okay, cool. Is asking about calculus 1 questions. What calculus 1 questions would you like to talk about? And, once you get that expression, all you have to do is just plug it in and make the eigenvalues pop out. The fourth one for calculus 1. Yeah, prove that it does not have a local maximum value at C. Yeah. Anything specific on this? I think we covered the intuition on the previous session. Do you have any particular questions about it? You can also feel free to hop on voice chat if you so please. If you'd rather talk about it via discussion. Do you all usually do homework on Friday nights? My first semester of school, every single Friday night was just reserved for writing up my lab report. Every single Friday night. Yeah. By the way, folks, for the sake of growing this platform, can I ask you to make sure to like the stream when you're watching it, as well as subscribe? Sorry to be obnoxious. You're in voice chat. Okay, let's talk. Hey, what's up? Can you hear me? I think you're muted right now.
Hey, can you hear me?
Yes.
Yeah, what's up?
Hey, hope you're having a good day.
Yeah, pretty good. Pretty much everything is on track until now.
Cool. Would you say that the calculus class has been like pretty chill lately? Like, I know the first homework everyone was panicked about, but like I feel like things have mostly come under control since then, right?
Yeah, I think the assignments are now like doable.
Yeah.
We are used to it, I think now. Earlier, first time it was just shocking, the what is this?
Right.
Yeah. So, I mean, I think I'm talking about the fifth question. Like, should I give a normal example? Anything?
Of
Just
question 5?
one function. Yeah, the fifth one. The one
Gotcha.
function f just touches the maximum at critical point, and another g just crosses it. So I don't know. Like, should I give the random examples, or do I need to give a specific expression of an equation?
I would say a single counterexample should be sufficient to show why the result fails if you don't have differentiability. Yeah.
Okay, I don't know if I'm giving it out, but is it means that we're unsure about the continuity if both the functions are
No, I
differentiable?
think we're guaranteed the continuity. Otherwise, the question would just be a little nonsensical. But like I think it's understood that they're both continuous, at least at point C. Just f is no longer differentiable. Does that make sense?
Yeah, but I'm looking for the counterexample. Is it like you're telling me just we take two functions that are not differentiable, right? As a counterexample.
Right. So if it's not differentiable, we get a lot more power to make things kind of nasty at that point.
So if it's not differentiable, so we cannot do like addition of the functions.
Well, we
We
can
can
still
do,
add
but
them. We can still add them. It's just a matter
we
of
don't know. Yeah, we don't know if it's like differentiable or not.
we don't really care whether the sum is differentiable or not. We just care whether or not the sum has a local maximum.
Oh, okay. Sure.
Okay.
Yeah,
And
got it.
remember the line of thinking I was suggesting was if f is no longer differentiable, think about having giving it a really sharp corner or a cusp.
Mm-hmm. Yeah, I remember
Right.
this
And see if that can
relation.
lead you to a f plus g that does not have local maximum. I would advise
Okay.
the steeper the better.
Yeah.
The steeper, the more obvious it is.
Mm-hmm.
Mm-hmm.
Yeah, makes sense. Makes sense.
Yeah.
Nice.
Any other questions?
Thank. No, I was just a bit confused with the example.
Sure. Sounds good. Mm-hmm. Anyone else have questions?
Yeah, I can hear you.
Yeah, I think most people have more or less left for today. It seems like
Oh,
yeah, I was expecting it to be a quiet session. It was just a small handful of people who wanted to ask questions. But feel free to keep asking if you have more stuff. It doesn't seem like there's any other active questions.
yeah, I'm pretty much
Oh,
solved most. But I think third one is
so
I
your
think
mic is
the
going
only
in and out. What's up?
okay, so I pretty much got all the questions, but with the third one, I'm able to just find the modulus error.
Gotcha. Oh, I'm seeing some half and halves question where they're finding AX. Well, remember, if you know what X is at this point, right? You've expressed X as a linear combination of V1, V2, and V3. Well, then just plug that in. So replace it with C1, V1 plus C2, V2 plus C3, V3. Yeah? And then start invoking linearity to separate these up and pull the constants out. And then use the fact that V1, V2, and V3 are eigenvectors to, remember, V1 is equal to lambda 1 V1. Start using all the tools you have from linear algebra to start splitting these things up and making it look nice and replacing A with lambda for eigenvectors. Now, what were you saying, Mukul?
Yeah, I was saying the third question, I was able to find only one error. Like, were you also able to find only one?
Let me
Or you
remind
were able to find...
myself. What question is it? Oh, is it under York students?
Yeah.
Okay. Yeah, I didn't look over this one too carefully, but yeah, for me, I think I just saw, one big error.
Yeah.
It's yeah, right. It's this,
Modulus one, Eric.
huh? I
The
don't want to give
mod
it.
thing. Okay,
I
okay,
don't want to
sure,
give it
sure,
too far
sure.
away, right? But like
Oh,
this,
sure, sure.
this issue where they
I
have
understand.
something that looks like this absurd thing, right, from 0 to pi, I think.
Yeah.
Right? They try to claim that everything is constant because the endpoints are equal, and because there are no critical points in between. Yeah.
Mm-hmm.
But like,
Yeah.
what the heck is this point? What the heck is this point? So
Yeah.
you just got to think about how they like fail to account for what's going on there.
Mm-hmm.
Okay, regarding the linear algebra question, I did go over the linear algebra question with someone named Emily earlier. What linear algebra question are you wondering? Like, I would have been happy to schedule a linear algebra session. It's just in the past when we did it, nobody would show up. It was seemed very pointless. Going over question 6b on the theoretical calc, how does one approach it? Yeah, that one I haven't worked out myself because I feel like I can't, I don't want to give it away. But okay, how do we think about it? You would probably start by taking the derivative, which, okay, let me do that in my head. That's annoying. It's easy. 2x. What does that derivative look like? It would be something like 1 over 1 plus fx squared. And then chain rule, product rule. Minus x over this thing squared. This is just terrible. This is awful. Times what? 2fx? Oh, I guess it should be f prime of x. F prime of x. F prime of x. Yeah, no, this makes it reasonably clear, I think. I think what you have to argue about is, look, when these two things come together, it's positive, right? It's positive because it gets squared. And the idea here is that the sign of these values basically only depends on f prime. Yeah? Basically only depends on f prime. Something like that.
Are you discussing the sixth one?
Yeah, I'm just thinking about what's going on here.
Yeah, I mean, just take f prime common. You'll get this like step.
What's up?
Take f prime as common, I think. Then you'll be able to like match with the statement.
Yeah, so the f prime is common, so I think you've got to show that f prime of x times times the rest. I think the idea is if you can show that f prime times the rest, if you can show that this part is like, if you can show that it's consistently positive, I think you're golden, right? If you can show that all the rest of here is like always positive or maybe always negative, I forget which, but you should be able to conclude that, at this point, if this stuff is like always positive, like its magnitude can fluctuate a bit, but if it's always positive, then f prime of x should totally dictate, should totally dictate like f prime of like capital F prime of x. Yeah. And like a maximum is a maximum is sort of when f prime goes from positive to 0 to negative. Yeah. And if you have a relationship like this, that should conclude all you need. Because when f prime is positive, capital F prime is positive. When there's 0, it's 0. When it's negative, and so on and so forth. That's that's the idea. You got to show that, you got to do the work yourself, but you got to look at this stuff sorry, you got to look at all this nastiness and see if you can factor out the f prime of x and see if you can conclude anything about its sign. And they give you a handy piece of so half and half is saying half and half is saying you double checked your work, it looks fine. Okay. Linear algebra. Have I done Q1? From which homework are you talking about? Which homework are you talking about? Anyways, let's see. Comment is saying to calculate AX. I mean, yeah, it's exactly the same idea. You just gotta plug in your combination C1, V1. Are you sure about like your C1 and V? Are you sure about your C1 and sorry, are you sure about your coefficients? Because that's a potential source of error. But when you have this V2, you can just split it apart just fine as you please, right? This you should be able to split this up into like C1 A V1 plus C2 A V2 plus C3 A V3. And at this point, you should be able to replace all the A's by your eigenvalues and see what that gets you. Yeah, we already did calculus. I've started a new policy of limiting the VODs to about 3 days, and we did them on Monday. You know, the idea behind this platform is about live learning. And it just seems like keeping the VODs up are disincentivizing people from showing up to the actual sessions themselves. So, yeah, sort of a difficult position where the fact that the VODs stay up seems to make it so that people don't really show up anymore. We could possibly organize another session, but sorry, we could perhaps organize another day. But you know, right now we've already covered the calculus material, and I like, how can I better communicate that these sessions are going on and that the VODs are, you know, only up for a limited amount of time? Because it seems like a lot of people are just totally missing the announcements and totally missing when things are scheduled. Yeah. So, I mean, this is literally your expression for x, right? You should have gotten an expression for x, and you should have an expression for x, and you should be able to literally express it as a linear combination of eigenvectors v1, v2, and v3. And you at this point, you should be able to invoke linearity to separate out each of these terms.
I think
and then
you're
pull
not
out the
streaming
linear.
this on YouTube. It's not streaming on YouTube.
Wait, this is not streaming on YouTube right now?
No, the explanation you're talking about is not.
Wait a minute, really? Why not? I'm pretty sure I'm still live, right?
Yes, but this window of OneNote is not.
Really?
It's not. Yeah.
No, I see it live on YouTube right now when I move the screen. Double check your own internet connection.
Oh yes.
Yeah.
I think now it's good. Yeah.
Gotcha. You got 3, 1, and 3, -1, and -7 for your coefficients? That doesn't sound. That sounds too complicated. Just double check. I mean, can you double check that that's even right in the first place? 3 and -7. No, that's that doesn't seem right. What the heck? Oh, for your AX. Gotcha. For your AX. Well, I don't know. I haven't done the work myself. I think you got to go double check your calculations then. Are you sure that your coefficients for your X, sorry, your coefficient for your V's are correct? You 1, 1, and negative 2. One, and negative 2. Two. Yeah, I agree with your C values, sure. 1, 1, negative 2. Well, okay then. 1, 1, negative 2. And what the heck are your eigenvalues? 1, 1, negative 2, you say? So then this should be lambda 1, lambda 1, lambda 2, lambda 3. So what does that look like? Negative 4? Negative 4. Lambda 2 is 1. Lambda 3 is 2. So this looks like coefficients of negative 4, 1, and negative 4. 1, V2, V3. Okay, so to me, this looks like my first answer is going to be... I mean, I'm just getting a different result from you. 1, 1, negative 2 is correct. I mean, I'm just looking at this, and my first, my top row looks like negative 4 times 0, 1 times negative 1 is negative 1, 4 times negative 2 is 8. I mean, to me, it looks like I'm just getting, I'm looking, when I try to calculate AX in my head, I'm getting totally different results from you. Yeah, just write this out and multiply it. It's, and add them up. Yeah, I disagree with your answer. 3, negative 1, negative 7. That just doesn't look right at all. Go double check what you're plugging in here. Yeah. Negative 4 is 8. Okay, anyone else have other questions?
Hey there.
Sure, what's up?
Yeah, so if I think there are not many people, and if you're not busy, could we like discuss with some data structures problems?
Sure. Yeah, let's think of a good data structures problem.
Okay.
So this one might be a little bit tricky, but do you know what an H index is in academia?
H index, I'm not sure.
Yeah, go look up the definition of H index.
Are you talking about each index or
No,
H
like literally
index?
the letter H index. This is something that physicists, mathematicians, academics use to indicate like their academic, how prolific their academic output is. It's sort of, if I remember correctly, it's like the number of papers you have greater than the index of the paper. So it's like if you had maybe parse the definition yourself, but if you had someone with like a paper with 10 citations, 9 citations, 8 citations, etc., it's basically like if you plotted it, the index increases linearly because like the index is 0, 1, 2, 3, right? The index increases linearly, and the citations decreases if you put it in descending order. And the H index is basically where they intersect.
Okay.
Right. So the question is, given an unsorted list, find the H index. Group read,
Okay.
what's up? I see you've joined the voice chat. And for Kai's asking about question 1 from linear algebra, is this the Vanderbilt matrix stuff? I guess so. I'm just I'm a little bit frustrated by the redundancy because how do I put it? I like to synchronize these things so that everybody shows up for these sessions, and I keep the VODs around for a few days just in case people really can't make it. But I don't know what the right solution here is. It feels like keeping the VODs up for too long is disincentivizing people from attending the live sessions, and that's the whole point of the teaching here is live instruction. I'm not really fond of the idea where students are skipping out on the entire sessions and just looking through the video trying to, pull stuff out. So, I mean, I guess I could do one more session for homework 4, but that would probably be it, with the understanding that in the future I would only do, one session per homework, because I, don't like to repeat myself, and also I think that keeping the VODs up is hurting, people actually learning these things to their fullest potential. Yeah, we can talk about the VOD thing real quick, but yeah, because it's, we're sort of going through these growing pains, I could do one more session on on the calculus homework 4. I just would have to arrange it so that people would actually show up. And, during the earlier part of the semester when the homework was really hard, it seemed like whenever, we did a session, everyone would show up. Nowadays, people don't seem to be, remotely as motivated. And, okay, so with the Vanderbilt matrices, yeah? Let's take a look. Vanderbilt matrices. Let's see. Okay, Vanderbilt matrices. Yeah, so if I remember correctly, you show that V4 is equal to LU. Well, like, you literally know what all the matrices are, right? You can just write out what V4 looks like based on the definition, and you can just multiply L and U together. You can literally just multiply these together and verify that it checks out. Yeah? And the spirit behind this problem is that it's really hard to calculate the determinant of the Vanderbilt matrix directly, but we know that the determinant of AB is equal to the product of the determinants. Yeah? And this is really nice. This is really, really nice. Because for this particular problem, the determinant of L is not so hard, and the determinant of U is not so hard. And that lets you skip around the really, really complicated matrix calculating the determinant of V4 directly is terrible. But calculating L and U, their determinants independently, is great. So that's the idea here. You can basically get around the really nasty calculation by multiplying together two really simple ones. And as for the polynomial interpolation stuff, honestly, I don't really remember it all that closely. Your textbook should have some very detailed examples, I believe, about how to do polynomial interpolation. So I would suggest taking a look through them. And I mean, the general gist here is that, a straight line, any 2 points you can make a straight line through, right? That's a p of x degree is equal to 1. And for any 3 points, you can put a parabola through it. Yeah, you can curve it back up. That's degree is equal to 2. And so on and so forth. And the idea here is that with what is it, like this? I think with n points, a polynomial of degree n minus 1 can interpolate them beautifully, can interpolate them exactly. And by interpolate, they basically mean just draw a polynomial to hit all those points. Yeah. It's basically the nastier the points are, the more curves are required in the function polynomial to turn around. And you get more curves and twists as the degree goes higher. Yeah, okay. Boy, I'm hungry. Question 4 on linear algebra as well. Gosh, why is everybody asking about linear algebra today? Is it due? Like in the past, when we did linear algebra sessions, it felt like basically nobody would show up. I mean, I'm happy to do them if you could get people together. What is it? Are you asking about the Markov chain question about the steady state? Yeah, sure. Ask a question and I'll help. But Dominic, are you asking about the steady state question in linear algebra? Because, yeah, diagonalization is just going through whatever that process is. And the reason diagonalization is so nice is because, right? Yeah, sure. Wait, what? The reason diagonalization is so nice is because it's like D and then like matrix, I'll call it A, and then D negative 1, right? So if you raise this to some high power, like to the nth power, the thing is when you put, D, A, D negative 1 next to each other, the D and the D negative 1 cancels out. So this means that the A's get to just raise in power really simply, right? So raising the diagonalized format to the nth power just basically becomes this thing, right? So if you just calculate the diagonals, the diagonal, what do you call these things? The diagonal helpers beforehand. This lets you bump A to the n to the high power really, really quickly. Because remember that if A is diagonalized, it looks like A1, A2, and A3, right? And the rest of them are zeros. 0, 0, 0, 0, 0, 0. And this lets you just raise each one of these to the nth power. Yeah? That's the idea. Anyways, for Hazik, yeah, feel free to go ahead and ask your math question. We have a Discord if you'd like to ask your question, by posting it on the channel, or you can just take a screenshot and put it on Imgur, link to Imgur. Okay, folks, what can I help with? What questions do you have? Nothing. Google, are you having any success with that problem?
Yeah, I'm just thinking of solution like the
Sure.
force even.
Like, what's the brute force most obvious way to do this?
I think plots. I'm not able to think of like.
Okay, you can keep thinking.
I'll choose version combinations and all the I'll put all the permutation combinations.
Sorry, your microphone is really choppy. I can barely hear anything.
Can you hear me now?
Yeah, that's better.
Okay, so brute force would be the recursion, I think. Put all the permutation combination in C. if that crosses that line.
Yeah, I wouldn't call it recursion. So like I'm telling you that the list is unsorted to begin with, right?
Okay.
And so to
Sort it up.
yeah, exactly,
Like
sort it
descending
first.
sort?
Huh?
Descendingly. I'll sort descending.
Yeah, exactly. Yeah, I see the question. Is this a high school question? That in a polynomial, development or independent term is 1 followed by x to the naught with x different from 0. Having said that, what is the independent term independent of x in the development of... Oh, okay, gotcha. Yeah, this seems like this is just a good application of binomial theorem, right? So this is basically saying x squared, no, sorry, plus 1 over x to the 6th power, right? And the idea here is that you got to think about all the ways in which you could choose. You got to think about all the ways in which you could choose. What is it? X squared twice, and choose 1 over x 4 times, right? So think back to your binomial theorem, because if you choose x squared twice, this becomes x squared squared, and then you multiply that by 1 over x to the 4th. And this is x to the 4th over x to the 4th, and this is equal to 1, right? So this is basically saying, okay, now you got to use your binomial theorem, right? Sorry, you got to use choice. So it's like, okay, 6 choose what will give you 2x squared, or 6 choose what will give you 4 1 over x. So yeah, I understand the problem. You just got to, and I can give you a hint that you want to use the binomial theorem and figure out how to get the right number of choices of x squared or of 1 over x to the 4th. So think that through. Now, what were you saying, Bukul? Hello? You there?
Yeah. Yeah. Can you hear me?
I can. What's up?
Yeah. So I think I have to see whether this. I have to see like if what's the first element that crosses the line, that kind of thing, and that element that crosses the line, that's gonna be the element before that could be my answer. Like I have to find like first element that crosses the line, so I get the summation. I'm thinking right?
Yeah, if you it's like, so hold on. If you basically sorted it, right, this would make everything pretty easy, because you could just figure out
Yeah.
where one line crosses the other, right?
Yeah.
So the question is, how do you do this? Like, what runtime is sorting?
It's the fastest is n log n with one space of 1.
Right. Can you do
Yeah.
better than that?
Okay. So
By the way, who else do we have with us here in the voice chat?
Yeah, it's me. I just wanted to ask a question that's not really related to like math per se, but
Yeah.
I feel like it's for you know how you did like the calculus session from November 8th?
Yeah.
I wasn't able to watch it because I've been like very busy this week. So is it possible for you to make that YouTube video public?
Right. So we had another student asking about this as well. We made a pretty conscious choice to limit VODs to a couple of days, because we think that keeping the VODs up sort of disincentivizes people from showing up to the live sessions, which is the whole point of the platform. We keep the VODs up for a couple of days because we understand that some people ultimately have work or just can't make it in one particular night. But it's a kind of thing right now where we want to do a better job of making sure that people actually hear when these things are scheduled, because right now it seems like there's very little engagement. When I organize these sessions, not too many people show up anymore, and I think that kills the point. I think that starts to hurt the point of the platform. as opposed to like the first couple of weeks with those calculus problems where, when we do a session, basically everyone would show up, right? I think people are getting too. I kind of feel like people are getting too dependent on the VODs. Is my hunch here.
So you're not gonna do that?
Yeah, what we could do instead is we could host a second session for the calculus questions.
Yeah, that would be great. Yeah, that would be
But
great.
in the future, I'm basically looking to. I would basically do a homework session just once and keep, or a problem session just once, keep it up for about 3 days, and you basically gotta. I think you basically gotta either make it live or during one of that period, because I think if we don't take advantage of the fact that this is a live learning platform, I feel like there's very little point to it. You know what I mean?
Yeah, I get it.
Yeah. So we can make an announcement to do a second session maybe on a Sunday. And that'll be it for this particular homework. For future homeworks, where I guess this is almost like a grace thing because
For the session that you're doing on Sunday, it's about assignment 3 for 1013, right? Because I'm really having trouble with that.
Wait, 1013? Oh, wait, this is applied math, not theory math?
No, not theorem. It's applied calculus, because I'm having like a lot of trouble with assignment 3, so
gotcha.
I could,
we did applied math and theory math on like the same day, and I think not more than like 2 or 3 people showed up for the applied math section. Are people having trouble with it? Because I'm let's see, what do you call it? I remember that for the previous session, for the previous homework for applied math, a bunch of people showed up. But for this one, it was like less than 3. And it, when that's the case, it kind of feels pointless on my end. It feels like a big time commitment for, not really benefiting many people. I don't know. Are people still interested in, in help with applied math? This is the one about the Mercator projection, right?
No, I don't think so. It's about related rates and all that.
It's about related rates. Yeah. What the heck was you said question 3? What's the problem?
Hold on, let me bring up the PDF real quick. It's like something about like 2 colored pencils, like red and blue, something like that.
Oh yeah, no, that's question 1, right? 2 colored pencils, red and blue. Yeah. Yeah, that's right. That's from the applied math set.
So would you do a stream like going over like because I'm kind of having like trouble like understanding like how to do the questions, so
right.
Is it possible for you to do a stream like going over them?
I mean, that's basically what we did on the last Monday. With applied math, it seemed like basically nobody showed up for the last session, so I'm theory at least a couple of people did. With applied math, it was so few that I'm wondering if it's even a point. I don't know. This is a relatively big class, right? Do you get the sense that people are just not struggling with it, or?
I don't really know about like how other people are doing, but like I'm kind of struggling with it. So.
Okay. What does this thing do? When does it do?
It's due Sunday, November 14th.
Oh, okay. So in about 2 days.
Yeah.
Okay, I could do a. Sorry, is this one of those things where it's like technically due today, but you get a 2-day grace period or something?
Yeah, it's one of those things.
Okay. I don't know. It doesn't seem like there's probably enough like runway for a second session to be worth it. I guess I can unprivate the video for like a for like the rest of the evening, and that's about it.
Yeah, thanks. That'd be so helpful. Thank you so much.
Like, yeah, in the future, try to let your friends know, or try to let people know to attend, because Like, it feels incredibly pointless to me when I do one of these sessions and no one shows up.
Yeah,
And,
I'll make sure to do that. Yeah, thank you again.
Hello.
What's up?
Yeah, I would like you to just explain the question with an example, so I can confirm like the thinking.
Sure.
Yeah.
Question with an example. So, like, if I gave you a list like, I don't know, 10, 11, 7, 3, 5, maybe?
Okay.
The idea here is the index would be 0, 1, 2, 3, 4, 5. So then the base value would be 11, 10, 7, 5, and then 3. So I think the H index, what is it? I forget the exact wording, but I think it's defined as like the largest index that's smaller than the associated value. So I think the H index here would be 3.
Okay. Can you repeat the last definition?
Yeah, there's a bunch of like very similar definitions, but the one I seem to recall is like the largest index that's smaller than its corresponding citation count. So here,
Okay.
3 is less than 5, but 4 is greater than 3. So this is the cutoff. This is the H index.
Okay, so it should be. I mean, x value should be less than y value. Is that what you mean?
Yeah.
And what about? Okay, so if let's say it would have been instead of 3, let's say there would be. Take an example of 7, or maybe 4.5 instead of 3. 4.5. So
4.5. Okay.
so this is the answer. Then 4.5.
Yeah, then I think the answer would be 4 because it's smaller than its associated citation count.
Oh, okay. So I think we just need to find. We'll sort it out, and we just find the value of the array, which is less than the index,
Right.
and we can do it in multiple ways. And the one is using the loop, correct? The
Right,
O
right,
of
right.
n.
If it's already sorted
And
at that point, if it's already sorted
and
at that
another
point, there's
one,
nothing to say.
yeah. So the overall complexity would be n log n,
Right, and I'm asking, can
and
you do
space would
faster than
be.
that?
I mean, if it's already sorted, like the question is, the given is sorted, or I'm not sorting, right?
No,
If I
I'm
don't apply.
giving the array to you unsorted, and I'm asking if you can still do better than n log n.
Okay.
Yeah.
Oh wait, it's. I do have to sort it. Are you talking about like I don't have to sort it?
Well, I'm going to let you think about that.
I mean, if I sort it, I can also use what do you say? I think binary search, which is log n, to get my answer, but overall complexity will be n log n.
Right. So
But yeah.
basically, can you do better than?
Okay.
That?
Let me think.
So someone is talking about linear algebra, still having trouble. Okay. Find two different diagonal matrices D and the corresponding matrix S, such that A is equal to S D S negative 1. Interesting. You can diagonalize it in two different ways. I didn't know that. I mean, stupidly, you could just Honestly, I don't know. I didn't realize that diagonalization was non-unique. Oh, yes. Okay, no, that's not too bad, right? So if the diagonal matrix, if I remember correctly, was like eigenvectors x1 and x2, right? You should be able to just redo it differently as x2, x1. So if you have one answer, you should be able to generate the other as well. You see what I'm saying? Wait, am I thinking of the right thing? I'm pretty sure the eigenvectors, or is this supposed to be S? Is this supposed to be S? Yeah, I don't remember this off the top of my head. Let's still look at diagonalizability. Diagonalizability. Find the distinct eigenvalues. Compute a set of basic eigenvectors corresponding to each of the eigenvalues lambda. The matrix A is diagonalizable if and only if there are n basic eigenvectors in all. So if it's diagonalizable, then n by n matrix P with these basic eigenvectors as its columns is a diagonalizing matrix for A. Gotcha. That's awesome. P is invertible. Yes, so it sounds to me like if you're constructing the, so you can go through this process to construct the eigenvector, yeah? And from there, I think you should be able to figure out what D is. Yes? But my hunch is that if you figure out, if you do one orientation of S, you should be able to do the exact same problem by flipping the orientation x1 and x2. And I think that should be able to generate a different answer for you, I hope. Are you sure it's not right, or is this just a computation error? Okay, let's look at the picture. I'm looking at the picture. What is your matrix diagonal? I mean, are you sure you didn't make just some calculation error? 2, 1, 3, -4, 8. The red outline means that it's wrong. I can't tell what's red here. I'm colorblind. I don't know. I'm double checking this on a. I double checked this on a matrix diagonalization calculator. And it looks to me like D is equal to 5004 is perfectly valid. It looks to me like you're. Do you have to normalize the values of P at all? Does it matter if your eigenvector is not normalized? I don't know. If S1 also looks fine to me. I mean, could it be as dumb as corresponding matrix S? So if we tried something like this, and we flipped it around, what do we get for D? Can I go over countable infinity? I guess so. What are you trying to ask? Like the short answer is that you can just put it in bijection with the natural numbers. -8. I don't know if you're telling me that literally, even the answer of 5 and 4 is not working. That's weird. That you might try putting 5, you might try putting 5 and 4 into D2 instead to see if that works. But other than that, it's definitely at least one of the valid Ds. Yeah, at that point, you might have to talk to your professor to figure out if there's something wrong with this or if there's some special formatting they need you to obey. How do you go about it when you're trying to prove it? Well, okay, let's say that you had some example like, I don't know, all the multiples of 5, right? 5, 10, 15, 20, etc. And you wanted to put it in bijection with the natural numbers, 1, 2, 3, 4, etc. Right? The intuitive way is to just sort of do a correspondence between the two of them. But to do it rigorously, you have to say that the function f that maps the natural numbers to these, or vice versa, so some function f between the two sets is such that f is bijective, right? Which means that it's 1-to-1 and it's onto. So you have to show both properties. These are also called injective and surjective. It's the same concept. Injective, surjective. Yeah. So remember, try to recall what injective and surjective mean, or one-to-one and onto, whatever your class terminology likes to use, and show that some function f that maps between the top set to the bottom set is a bijection. That's the idea. That's all. For linear algebra, I mean, think it through. It's literally asking you to show that v is equal to lu, right? Like, and you have v, you have l, and you have u. So yeah, just perform the computation. And if Ferris is saying, if you're trying to prove the set of negative integers, is it fine if I map onto negative numbers as well? If you map onto natural numbers as well? Yeah, sure. I mean, you can use for comparison, the natural numbers are countably infinite. The non-negative integers are countably infinite. The regular integers are countably infinite. You can use any of them as a baseline, right? You can use any of them as sort of a comparison, so to speak. As long as you can, for a given set x, as long as you can demonstrate some bijection between x and any countably infinite set, then x is countably infinite. You can choose whichever set you'd like to compare to. Just choose whatever one makes the most sense to you. Choose whatever one's easiest. No? Sure. Coco Cat. Sure. Which problems would you like to take a look at? Or CCAT? Problems, conjectures, and proofs? Oh, interesting. Yeah, let's have you post some questions on our Discord where it says we have a channel called Intro to Proofs. Let's take a look at some questions. By the way, what school is this? Oh, do you need our Discord link, or do you have it? Okay, intro to proofs. Prove or disprove the following statements. Let a, b, m, and n be integers with m and n greater than 0. Okay. A is congruent to b mod m. Then a is congruent to b mod mn. Okay, that's kind of interesting. Okay, so how do we talk through these problems? I think you basically just got to come up with some examples and counterexamples, right? By the way, is this an intro to proofs class? Is this like, I don't know, how is the homework for this class? Is it good? It's called something different. Sure, okay. Well, the idea here, I don't know, let me try something crazy. What if we let m is equal to 1? What if we let m equal 1 and n be some other number? Does that make it clear? Does that give a big hint? Problems, conjectures, and proofs? Okay. What happens when you let it equal to 1? What implicate, I think that should make things kind of clear. Like, choose a very different a and b, and choose an n greater than 1, and see if this makes the situation just shine some light on the relationship here. It's a little bit weird to do mod 1, but, take my word for it. Or you could do it mod 2, just like choose m to be some really small mod, for example, and then maybe choose n really large to kind of get some intuition about what's going on here. Is there any method for writing this proof? Well, first of all, do you believe that this is true? If so, you've got to do a proof. If you don't believe it's true, then you've got to find a counterexample, which can be a lot more succinct. Counterexamples, maybe not quite as a rule of thumb, but are frequently very, very short if you've got a counterexample in mind. Oh, cool. Are you making any progress on that, thinking through that problem?
I'm still unable to optimize the n-log n solution.
Yeah. Let me ask you this: are you familiar with any sorting algorithms that are faster than n log n under certain conditions?
Okay. Is it, I think, quicksort?
Quicksort is still n log n and sometimes n squared. Quicksort is really good in practice, but it doesn't have any particularly good theoretical guarantee.
I don't remember exactly like the complexities, but I studied like merge sort and insertion sort. I don't remember the time complexity of
merge
insertion.
sort is still n log n. Insertion sort is n squared. Have you learned about any linear time sorting methods? Now, linear time sorting methods do not work generally, but work with some constraints in place.
Is it like bubble sort that works?
Bubble sort is still n squared.
Yeah, it is n squared, but I think the bubble sort is implementation when you use the STL, right? The standard template library sorting function. So if you have elements, I think less than 10, so it is implemented using bubble sort because
yeah, sure.
As far as
so very small values, sometimes n squared algorithms can be really fast.
Okay.
So think about that a little bit, and maybe look up, maybe make this a learning time too. Maybe look up some constant time sorting algorithms that might be relevant here. But this problem is very cute, and it took me when I saw it, it took me over the course of a lunch with a coworker to think through it. This was when I was interning at a place, and I thought it was cool, and I think this is one that you should mull over a little while. But for CCAT, if you let m is equal to, let's say m is equal to 2 and n is equal to 100. So then let's say you have a situation where a is congruent to b mod 2, right? And let's let a and b be super different numbers, like 2 and I don't know, 44 mod 2. Okay, well, these are indeed congruent mod 2, right? Because they're both even. But what about mod m times n, which is mod 200? Are these still congruent? Think that through. Think that through. Okay. I'm pretty tired. Maybe I should go get some food for this evening. Well, sure. I'm not saying anything crazy. It's just, okay, let's say that 2 is congruent to 44, mod 2. Yeah? Mod 2 is, what do you call it? When you are taking something mod 2, you're basically just sorting it into evens and odds. Now, what about mod, let's let n is equal to 100, mod 200 now. Is 2 congruent to 44, mod 200? That's all I'm getting at here. Can you see the idea? Just curious, what exactly does a Vanderbilt matrix mean? I was not familiar with it off the top of my head myself, but what exactly is its use? I mean, they give you the definition right there. I just don't understand. I don't know the bigger motivation off the top of my head. We can look it up. I'm sure it's useful for something. Vanderbilt matrix. I mean, it sounds like it has some deep relationship to the polynomials. Yeah. Matrix with the terms of geometric progression in each row. Okay. And its determinant is the product of xj minus xi for, I think, every possible pair. So yeah, it's this type of matrix with a bunch of nice properties. There's no point, or I don't think there's that much point to knowing all these things off the top of your head, but you should be able to gain intuition as they're presented to you in a class. Mm-hmm. Maybe I should go get some food. I'm hungry. All right. Well, do we have any last questions for this evening? Are we getting close to wrapping up here? Alrighty then. I think we're probably done for this evening. Seems like nobody has any more questions. Take care, folks.